This video is about the importance of bead profile, how the height, width, and contact angle of the weld bead affects the weld strength. I made this video because a lot of these are poorly understood, so these drawings will hopefully clear up and make these important concepts a little clearer. This image represents the ideal weld in a fillet, which is going to be a perfect 45-degree triangle. And we can see that the contact angle, which is angle between the face of the weld and the base metal at the toe, is about 135 degrees. And that's fairly large, a fairly open, wide angle. And this allows forces to move from the base metal through the weld a very easy path. And that's very, very important here to keep in mind, that the weld holding the parts together is allow forces to move between these parts and transmit them through the structure and eventually into the ground. This drawing shows a weld bead that's got either excessive height or an excessively rounded profile, almost like an overlap, basically. And see here the contact angle between the base metal and the edge of the weld forms a very sharp wedge-like angle. And you think of it like a wedge forcing its way into the weld, and this is going to cause cracking and weld failure when stresses are applied to it. So this is just a quick recap of the weld bead proportions. In this one, an SMAW weld or stick weld. The rule of thumb is that the weld bead should be no more than 3 times the diameter of your filler rod and no more than 1/8 of an inch high. This is done because it is found that this proportion is really the ideal to allow the bead to cool at a proper rate, either not too fast or not too slow. So we always want to try and aim for this every time we're welding. Now, in a gas metal arc weld or a flux core MIG weld, the height is going to be the same 1/8 inch, but in this case, because the filler wire electrode is so much smaller, the maximum width is restricted to 1/2 an inch. So this is something to keep in mind. Whether flat or vertical, we want to keep within that 1/2 inch maximum. This is also going to allow the weld to cool at a proper rate, neither too fast nor too slow. Gas tungsten arc welds or TIG welds follow the similar rule to stick welding in that you're restricted to 3 times the diameter of the filler rod or an 1/8 inch height maximum. But because the filler rods are much smaller, this is something that needs to be paid attention to. For example, an average 3/32 filler rod means that your maximum width bead is going to be 9/32, or roughly just a little bit over 1/4 of an inch. So if you're using a much smaller filler rod, say 1/16, that means your maximum bead is going to be 3/16. If it's smaller than that, the welds are smaller. So this can be quite challenging, but must be adhered to in order to have proper bead cooling rate so it doesn't crack. Looking at this weld bead with a good weld profile, you can see that the contact angle very closely resembles the contact angle of the ideal 45-degree weld bead, in that it's a very, very open, broad contact angle that does not resemble the sharp wedge-like angle that is formed in undercuts, or when you have lack of fill, or if the bead has an excessive height or an excessive overlap on the edge. This is kind of what we're looking for every time we put beads down. That same damaging wedge shape in the contact angle can also be formed between beads. For example, in a multi-pass weld, it's very common for beads that are not overlapped properly to develop a deep crevice between them. And this also forms that very damaging wedge shape that under stress will promote cracking and failure of the weld. And this is to be avoided as much as possible. In these final two examples, in the top one, you can see that In a straight bar, the forces move through the material unimpeded and forces do not stack up or get caught at any sharp edges. In the bottom example, a wedge or a notch in the material, either formed by damage or formed by a too sharp toe in a weld bead, doesn't allow forces to move through the material. In fact, they get stuck, which causes a great rise in stress at this location, eventually cracks and failure of the workpiece. So this is an example of the notching effect. So this can either be, this is why you do not hammer welds with chisels or welding chipping hammers and damage the surface, because this notching effect, greatly magnified, is a little wedge that will start to form cracks and weld failure.